DeepSeek just dropped a math model that basically broke every expectation the AI community had about what open source could achieve. And honestly, the teaming couldn't be more perfect. We're talking about DeepSeekMath-V2, a 685 billion parameter based. That's 671 billion in the main model weights plus 17 billion in the multi-token prediction module that scored 118 out of 120 on the Putnam 2024 competition, crushing the best human score of 90 points by 28 points. And here's the crazy part. The weights are fully open under Apache 2.0 license, available right now on Hugging Face, meaning anyone can download it, inspect it, and run it locally. This thing hit gold medal level on IMO 2025, solving 5 out of 6 problems perfectly, matched Google DeepMind's official gold standard, and outperformed basically every proprietary system on proof-based mathematics. And the real breakthrough isn't just the score, it's how it got there. DeepSeek built a model that actually verifies its own reasoning, catches its own mistakes, and iteratively fixes proofs before submitting them. So let's talk about that. Alright, so DeepSeekMath-V2 landed on November 27th, and within hours, the entire mathematical AI research community was dissecting every detail. The model is built on DeepSeek v3.2 EXP base, which itself is a mixture of experts architecture with 37 billion parameters activated per token. The results speak for themselves. On the Putnam 2024 exam, which is the most prestigious undergraduate mathematics competition in North America, DeepSeekMath-V2 solved 11 out of 12 problems completely. The remaining problem had only minor errors, landing it at 118 out of 120 points. To put that in perspective, the top human score that year was 90 points. The median score across 3,988 participants was 2 points. The average was around 8. Most students walk out with 0 or 1 point because these problems are designed to break even the best mathematicians. And honestly, when you read that DeepSeek's model beat the best human by 28 points, it stops sounding like incremental progress and starts sounding like a completely different category of capability. But the Putnam score is just one piece. On IMO 2025, the International Mathematical Olympiad, DeepSeekMath-V2 achieved gold medal level by solving 5 out of 6 problems perfectly, earning 35 out of 42 points. That's the exact same score Google DeepMind's Gemini DeepThink and OpenAI's unnamed reasoning model both achieved. But here's the difference. Google's model required official IMO certification and took days of compute in some cases. OpenAI didn't even enter the competition. They just tested their model on the problems afterward. DeepSeek handed the community the ability to reduce results independently because early tests confirm the scores hold up when researchers run it themselves. On the Chinese Mathematical Olympiad 2024, DeepSeekMath-V2 fully solved 4 problems and earned partial credit on a fifth, landing it firmly in gold medal territory again. And then there is IMO Proof Bench, which is a benchmark specifically designed by Google DeepMind to test formal proof capabilities. DeepSeekMath-V2 hit 98.9% accuracy on the basic subset and 61.9% on the advanced subset. For context, that puts it just slightly behind Gemini DeepThink's 65.7% on advanced, but ahead of basically every other system by a massive margin. When you compare it to GPT-4o or Claude 3.5 Sonnet, which sit closer to silver or bronze class performance on proof-style tasks, the gap becomes obvious. This isn't a model that's catching up to the competition, it's sitting at the same table as the absolute best systems in the world. Now here is where things get really interesting. The breakthrough behind DeepSeekMath-V2 isn't just throwing more parameters at the problem or scaling up compute. It's a completely new training architecture that solves one of the deepest flaws in how AI models approach mathematics. Most recent batch reasoning models use reinforcement learning that rewards only the final answer. You give the model a problem, it spits out a number, and if that number matches the correct answer, it gets rewarded. But there is a structural problem with this. A correct numeric answer does not guarantee correct reasoning. The model might reach the right number through algebraic mistakes that cancel out, or it might hallucinate intermediate steps that having to land on the correct final value. And for tasks like Olympiad proof or theorem proving, there is no single final numeric answer. You need a complete argument in natural language, step by step, with every logical leap justified. Standard answer-based rewards simply don't apply. So DeepSeek flips the entire pipeline around and optimized for proof quality instead of answer accuracy. The system works through a verifier-first training pipeline. First, they trained a proof verifier using Group Relative Policy Optimization or GRPO, which is a reinforcement learning technique that DeepSeek pioneered in their earlier DeepSeekMath model. GRPO is a variant of Proximal Policy Optimization or PPO, but it cuts memory usage almost in half by eliminating the need for a separate greeting network. Instead of training a value function to estimate rewards, GRPO generates multiple responses to the same prompt and uses the mean reward of those responses as the baseline. This dramatically reduces the computational overhead while still giving the model strong training signals. The verifier they built doesn't just check if the final answer is correct, it reads the entire solution, scores it on a 3-point scale, and explains which steps are rigorous, which are incomplete, and which are flat out wrong. Basically, it mimics the way a human mathematician would grade a proof. But they didn't stop there. They added a second layer called a meta verifier. The meta verifier double checks whether the criticism from the first verifier is actually justified. This creates a two-stage feedback loop where the model not only evaluates proofs but also evaluates its own evaluations. And that's critical because as the proof generator gets stronger, it starts producing solutions that are harder to verify. If the verifier cannot keep up, the entire self-improvement cycle breaks down. So DeepSeek scales verification compute dynamically. When the generator creates a proof that's hard to verify, the system automatically labels it as a new training example for the verifier, which then gets retrained to handle that level of difficulty. This keeps the generation verification gap stable even as the model improves. The technical term they use is called star training, meaning the model iteratively generates its own training data instead of relying on massive external datasets of formal mathematical proofs, which are scarce and expensive to curate. Once the verifier and meta-verifier are trained, they use those as reward model for the proof generator. The generator is incentivized to identify and resolve as many issues as possible in its own proofs before finalizing them. The reward function combines three things: proof quality, agreement with self-evaluation, and analysis faithfulness. Essentially, the model learns to critique its own work, fix the problems it identifies, and keep iterating until it can no longer find any mistakes. This is such verifiable mathematical reasoning in action. And the reason this matters so much is that most AI systems today cannot reliably check their own reasoning, especially on open problems where there is no known ground truth. DeepSeekMath-V2 can. It evaluates proofs on their own terms, not just by comparing them to a reference solution. And honestly, when you dig into the IMO results, you start to see how that self-verification plays out. On IMO 2025, the model perfectly solved problems 1, 2, 3, 4, and 5. Each one earned a full 7 points. Problem 6 had hardest question on the exam, earned 0 points. And that's actually informative. Problem 6 is specifically designed to be nightmarishly difficult. Only 6 out of 630 human contestants got a perfect score on problem 6. 5 contestants achieved perfect scores of 42 across all 6 problems. DeepSeekMath-V2 hit the gold medal threshold of 35 points, matching the cutoff that 72 contestants achieved. 45 students scored exactly 35 points, putting the model squarely in the gold medal tier. And knowing where the boundary sits is just as important as knowing where the model succeeds, because it clearly delineates the current frontier of AI reasoning capabilities. On the Putnam exam, the breakdown is even more detailed. The competition consists of 12 problems, each worth 10 points. DeepSeekMath-V2 solved 11 of them completely, earning full marks on each. The 12th problem had minor errors, costing it 2 points. That's a 98.3% success rate on one of the hardest undergraduate math exams ever designed. For context, the median Putnam scores is usually 0 or 1 point. Getting a positive score at all is considered a commendable achievement. Scoring above 50 puts you in the top handful of competitors. And 118 points? That's beyond what any human has ever achieved in the competitor's 85 years history. 5 people have scored perfect 120s in total across all those years. DeepSeekMath-V2 came within 2 points on its first attempt. Now, the competitive landscape here is fascinating because this release landed right in the middle of a heated race between Google, OpenAI, and now DeepSeek. Back in July 2025, Google DeepMind officially entered IMO 2025 with an advanced version of Gemini DeepSeek and achieved gold medal level with 35 out of 42 points. The IMO coordinates certified the results, graded the solutions using the same criteria as human contestants, and publicly praised the clarity and precision of the proofs. OpenAI announced the same day that their experimental reasoning model also scored 35 points, but they didn't enter the competition. They just tested their model on the problems afterward using 3 former IMO medalists as independent graders. The timing of OpenAI's announcement caused some friction because Google had apparently agreed to wait until a certain period after the human results were announced before unveiling AI scores, and OpenAI posted their results just hours after the student winners were made public. Google made sure to highlight in their blog post that they were recognizing the significant accomplishment of this year's student participants by waiting until Monday. The competitive tension was obvious, but the thing is, both Google and OpenAI kept their models locked behind APIs or restricted access. Google's system is currently available only to trusted testers, and they are planning a broader rollout for mathematicians soon. OpenAI hasn't released their model at all and stated they don't plan to release a model with IMO gold level capability for many months. DeepSeek just dropped the full model on Hugging Face under Apache 2.0 license, and that mattered because researchers can now deploy theorem-proving tools locally, verify complex derivations in physics or biotech, optimize quantum algorithms, or even validate protein flooding math without relying on a cloud infrastructure that might be subject to data privacy concerns or geopolitical restrictions. Educators can build interactive tutoring systems that input a problem, receive a step-by-step proofs with critics, and adapt the explanations based on student responses. Enterprises can integrate these into R&D pipelines to accelerate scientific discovery in fields like cryptography, material science, or formal verification of software systems. Now, to be clear, this isn't a flawless system. The model still makes occasional mistakes, like making an extra lesson in medical scan examples or missing rare species identification details. It can't reliably handle clock times, which is a known limitation across all transformer-based models because they struggle with rotational reasoning and precise numeric encoding. And while the model excels at structured proof-based tasks, it's not yet ready to autonomously prove new theorems of significant mathematical importance. The Robbins conjecture, proved automatically by EQP in 1996 after resisting solution for 60 years, remains one of the few examples of a long-lasting open problem solved autonomously by AI. Time for gold medal status in highly elite competition doesn't immediately translate to world-class mathematician capabilities, but it's a massive step in that direction. And honestly, the reaction from the community has been overwhelming. On X, Hugging Face, Reddit, and GitHub, researchers immediately started dissecting the architecture, running independent evaluations, and comparing it to Google's IMO proof-based results. Some users pointed out that DeepSeekMath-V2 outperformed Google's DeepSeek model on the basic subset of IMO proof-based, which confirms the consistency of its reasoning across a broad range of problems. Others noted that while Gemini DeepSeek edges ahead on the advanced subset, the gap is still enough that DeepSeek is clearly in the same performance band. Meanwhile, general-purpose models like GPT-4o and Claude 3.5 Sonnet sit firmly in the mid-range, closer to silver or bronze class performance. The leaderboard essentially shows 3 tiers now. Gold tier with DeepSeekMath-V2, Gemini DeepSeek, and OpenAI's unnamed model. Silver to bronze tier with GPT-4o, Claude, and other strong general models. And then everything else. One thing that really stood out in the technical breakdown is how efficient the architecture is. DeepSeek V3, the base model, uses a mixture of experts' design with only 37 billion parameters activated per token. That means during inference, the model routes each input to a small subset of specialized expert networks instead of activating the entire parameter space. This drastically reduces computation cost while maintaining high performance. For training, DeepSeek V3 required only 2.788 million 8800 GPU hours, which is shockingly low for a model of that scale. Dense models like Llama 3.1405B require all parameters to be active during both training and inference, making them far more expensive to run. DeepSeekMath-V2 inherits that efficiency, meaning it can be deployed in production environments without needing massive GPU clusters. In fact, with the right inference optimizations, it can run on consumer-grade hardware at nearly 20 tokens per second, which is more than sufficient for interactive use. The other Another major innovation is the auxiliary loss-free load balancing strategy. In traditional mixture of experts models, you need auxiliary loss functions to prevent some experts from getting overloaded while others sit ideal. But auxiliary loss can hurt performance because it forces the model to use experts that might not be optimal for certain inputs. DeepSeek V3 introduced a bias term directly into the routing decision, dynamically adjusting which experts get activated based on the input characteristics without using auxiliary loss at all. This keeps the load balanced across experts while preserving specialization and performance. And because DeepSeek V3 doesn't drop tokens during training or inference, every piece of information flows through the system cleanly, which is critical for maintaining reasoning quality in long, multi-step proofs. The multi-token prediction objective is another piece that helps. Instead of predicting only the next token, DeepSeek V3 extends the prediction scope to multiple future tokens at each position. This defies the training signals, improves data efficiency, and enables the model to pre-plan its representations for better prediction of future tokens. For reasoning tasks, that means the model can think ahead multiple steps, evaluate different branches of logic, and choose the path that leads to a complete coherent proof. It's the difference between following a single chain of thought and exploring multiple possible solutions in parallel before committing to a final answer. And honestly, the fact that all of this is happening in China is worth nothing. DeepSeek is a Hangzhou-based startup, and they have been quietly building world-class models while leveraging China's AI ecosystem. They started with DeepSeekMath-V2 in 2024, which matched GPT-4 on GSM 8K despite having far fewer parameters. Then they scaled up to DeepSeek V2, which introduced the MOE architecture with 236 billion parameters and 21 billion activated per token. DeepSeek V3 pushed that even further, and now DeepSeekMath-V2 is sitting at the absolute top of mathematical reasoning capabilities. This isn't a fluke, it's the result of sustained research, smart architecture choices, and it directly challenges the narrative that cutting-edge AI can only come from Silicon Valley giants with unlimited budgets. That's where we will wrap it up. And one thing I'm curious about now is how this impacts the broader reasoning race. OpenAI teased that they will release a stronger version of their math model in the coming months. Google is expanding access to Gemini DeepThink for mathematicians. And DeepSeek just proved that the gap between proprietary and open source systems is closing faster than anyone expected. Drop your thoughts below. Make sure you are subscribed, hit that like button, and I will see you in the next one.